Thank you for inviting me. The title of my talk, as you can see, is Applications of Pump Probe to Measure Nonlinearity in the Earth. I'm going to start with some definitions and then talk about why we should study nonlinear elasticity in the Earth, then give some examples and talk about some current work, and then conclude at the end. So first, I'm going to define pump probe. Some of you may already know what this is, but just since it's in my title and I'm going to be talking about it, I figure I should define it up front. The goal of pump probe is really to measure the elastic modulus as a function of strain and the strain derivative of the elastic modulus, rather than what I'm going to call the apparent linear modulus. The apparent linear modulus is just what you would measure with a elastic wave travel time or some other kind of measurement like that, where you're not considering its sensitivity to strain. The way that you make this measurement in the laboratory is kind of shown in the schematic on the left. You have some kind of a material sample, and you're measuring the velocity across that sample. The S and the R stand for source and receiver. So you'd have a wave, a probe wave that's going across the material, and you'd measure the velocity across the material. And as you're doing that, you apply some kind of a force on the end. The material will deform in some way, so there'll be some strain imparted on it. And you would measure this velocity as a function of the different levels of strain. And this is done in the laboratory pretty regularly on both earth materials like rocks, and also on things like metals and other materials like that. And the reason why we might want to do this is because nonlinearity is a lot more sensitive to a lot of the things that we care about in rocks, particularly things like damage, permeability, porosity, poroelastic conditions. And so this is just a schematic of the different kinds of elastic measurements that you can make in the middle. And we have alpha, which I'll get into a little bit later, but that's a measure of nonlinearity. You have attenuation, and then you have what's labeled here as P, which is the P wave velocity. That's going to be measuring the apparent linear modulus. And if we have a sample that we have at rest on the left-hand side and a failure on the right-hand side, we can see that this alpha parameter changes by around 1,000 times or something like that, depending upon the material. And that's a much bigger magnitude of change than we get with the apparent linear modulus or even attenuation. So pump probe is measuring this here. Can you see my pointer, by the way?
Yes, we can.
Yes.
Okay, so pump probe is measuring this up here, which is a large relative change, and the probe without the pump part of it measuring the P wave velocity is measuring something down here, which only changes by some small fraction. So we can get a lot more information or a lot more sensitivity to material properties by measuring the nonlinearity. So I'm just going to go over some quick other definitions in terms of elasticity. Classic nonlinearity is basically Hooke's law with higher order terms. So F equals Kx or sigma equals M epsilon. So this is in terms of, if we want to think about it in terms of a tensor, this is related to anharmonic properties of materials. It occurs in single crystals and other intact homogeneous materials. We have hysteretic nonlinearity, which is elastic behavior with memory. And that's related to contact properties across material discontinuities. It only occurs in damaged, granular, or heterogeneous materials. We have fast dynamics, which is an instantaneous dynamical response of a system related to putting a material into disequilibria or a new equilibrium state. And then we have slow dynamics, which is a time-dependent process that's related to disequilibria and the process of reacquiring equilibrium. So this would be like material healing and things like that. So these concepts are primarily derived from physical laws and laboratory experiments. So why would we want to study nonlinearity in the Earth? Well, faults, fractures, pores, and grain boundaries are the source of nonlinear elasticity. We can use it to monitor systems regarding hazards such as earthquakes, porosity, permeability, and solid fluid interactions. It's related to permeability, stress, and material failure. The elasticity of materials is determined by grain properties, contact properties, and force chains. And we can leverage substantial laboratory and theoretical work on rocks. On the right-hand side, I have some zoom, kind of a thin sections of different kinds of rocks. And what you can see, of course, is that they're very heterogeneous. And so the elasticity that we would measure with a seismic wave, for example, will aggregate everything that we see in here. So each of these grains has some kind of elastic properties, but then we also have the properties of the contacts in between the grains and the geometry of it. And we also would have force chains that would transmit stresses from one side of this material to the other. And all those things contribute to the elastic properties that we would measure with an elastic wave. And so there's quite a lot of nonlinearity in rocks because of this structure that they have. And that tells us a lot about the things that we care about in rocks, which is stress and permeability and failure conditions and those kinds of things. So, but a major obstacle is making the same kinds of measurements in the earth that are done in the laboratory. So why are rocks nonlinear? I talked about that a little bit in the last slide, but the effective elastic modulus, so this is what I'm calling in my previous slide, the apparent linear modulus that depends on the grain coordination number, which is essentially how many other grains each grain is touching, the contact stiffness, the grain contact geometry, and all these are affected by the stress state, the porosity, the pore fluids, the elastic properties of the grains. So essentially each possible grain configuration represents a different elastic state. So we can imagine that as stress evolves, it affects the grain contacts and things like that, and that actually can change the elasticity of the material. We can kind of zoom out a little bit and look at the kinds of scales that we're typically dealing with in seismology. And in particular, we can look at a fault zone. On the left-hand side is a cartoon that shows you what a fault zone might look like. We have with damage being the greatest right along the fault and then decreasing as you get away. And so you can imagine that we'd expect different nonlinear behavior in the core zone than we would as we get further away. The width of this could be anywhere from tens of meters to hundreds of meters to maybe a few kilometers. To the right is just a picture of a fault zone that they were looking at in this paper, and we can see that some areas where they infer the damage zone to be, in the terms of maybe a kilometer or two wide, in other areas it's more narrow depending upon the geometry of the fault and things like that. And so we can measure the nonlinearity to get some idea of what's going on in the fault zone. So this is kind of a summary. We have linear behavior on the left-hand side, and as I guess the name suggests, we have a linear relationship between stress and strain. It's a function in the sense that if you know the strain, you know the stress, it's constant. This is what I would kind of call the apparent linear velocity, linear modulus or linear velocity. And we often assume that this is the behavior of rocks and behavior of the earth, but this is really not the case more generally. The other two kinds of nonlinearity are classical nonlinearity. That's just the same thing as Hooke's law, but with some extra terms, sometimes multiple extra terms. And so stress and strain still form a function, meaning that they're single valued at every value of stress and strain, but it's just not linear anymore. And then we have hysteretic nonlinearity, where we have this alpha term, which I pointed out earlier. And this is a coefficient to a function of both strain and strain rate. And this is where we get these kind of loops where we no longer really have a function, a single value function. There are multiple values of stress for each value of strain and vice versa. And so that this has memory in the system, it's path dependent, and it's this is really the behavior that all rocks exhibit we're often measuring it, simplifying it as linear or something like that, but we can learn a lot about what's going on by trying to understand the nonlinear hysteretic behavior of this alpha parameter. So as far as applications, the two I think most important, or at least ones that I've sort of thought about, are, can we know where in the slip cycle we are? So on the left-hand side, we have this schematic of an earthquake cycle. On the horizontal axis, we have the slip rate, and on the vertical axis, we have the shear stress. And so we have some kind of an interseismic period where the slip rate is very low, shear stress is building. We get to nucleation, and the slip rate increases, the shear stress hits some kind of a maximum, and then we have coseismic, which is the earthquake itself, and the highest slip rates, and then post-seismic, the slip rate decays, and we're back into the interseismic period. Now, the stress state is different on the rocks, the slip rate is different on the rocks. Can we see that in the nonlinear behavior? All of this stuff has an impact. Essentially, the internal contact properties are really important. And can we measure that in an earthquake cycle? Can we know at any point in time, can we measure a rock and say, oh, we're here in the earthquake cycle, or we're here, or we're here? It's not necessarily a technique to predict earthquakes per se, but we can maybe learn a little bit more about where we are in the earthquake cycle than what we know today based just on the statistics of past earthquakes. The other thing that I think is pretty important for a lot of cases, especially energy-related applications in terms of oil and gas, geothermal, CO2 storage, and things like that, is how do fluids affect contact properties and force chains? And can we know fluid and poroelastic conditions by measuring contact properties and nonlinear behavior? So you can imagine in a fluid-rich environment, whether it's water, oil, gas, CO2, would affect, most of that, the fluids would exist at grain boundaries and in pores and fractures and things like that. And it's certainly going to affect the contact properties, the internal contact properties of the material. And can we measure that and infer something about what the fluid conditions are? And so those are two really important questions in geophysics that I think can be addressed in part with measuring the nonlinear behavior of the rocks. So now I'm going to go into some examples at Earth scale. And what I'm using is a pump probe in the Earth. And so the way that this works is there are really different kinds of pumps that you can use. Anything from barometric pressure to thermal stresses and strains to hydrological kinds of things. I like to use the solid earth tides because they're predictable and they're repeatable, and so they're sort of easy to use in that regard. They're smaller in amplitude and some of the other effects, especially barometric pressure, but you don't have to. But it's a bit, they're predictable, the solid earth tides. That's why I find them to be useful. So the pump is related to mostly to do with the orbit of the Earth, the rotation of the Earth relative to the sun and the moon, but also the orbit of the moon around the Earth. And so this is what a typical solid earth tide looks like. The blue curve is the volumetric part of it, and the red part is the shear part of it. This depends upon the latitude and also on the orientation of a fault, if you're looking at a fault normal stress. And so you can see this high frequency part of it, which is about a 12-hour cycle that's related to the rotation of the Earth relative to the sun and the moon. And we have this other longer period beat that kind of goes up and down. And that's the orbit of the moon around the Earth. And that's about a 14.7-day cycle going from a new moon to a full moon and back again. And so we can use this as a pump to measure the elasticity at different strain levels. And the probe in this case, in the first example, is going to be an artificial probe. So it's going to be an artificial source to a receiver. But we could also potentially use empirical Green's functions as a kind of a natural probe. So this is a really interesting study where they looked at this, and I think it's sort of a little bit maybe underappreciated, but this is a study at Parkfield, California, and they're measuring travel times across two different boreholes. So at Parkfield, as some of you may know, they drilled right into the fault zone. It's called the Seyfod hole, and there were actually two boreholes. One of them was a pilot hole to kind of test a few things and look at the geology, and then the actual hole went down, and then they drilled at an angle down across the fault zone. But at one point, they put in a source and receiver in these two different holes, and then they measured the travel time between these two over the course of a few weeks, I think it was. And they happened to catch a couple of earthquakes. The hole, looking at the map view, was a little bit off of the fault, and they happened to catch a couple of earthquakes. There's a magnitude 3 and a magnitude 1, and I'll show you a depth profile next so you can see how far away it was. But they measured that the velocity sensitivity to barometric pressure was the biggest effect, and much bigger, for example, than the earth tides, and this was the number that they got. So what they did was they measured delay time. So on the left-hand side, we have like a cross section, and you can see that the hole itself is pretty shallow. It's, it's only like a kilometer deep or something like that. And then the smaller earthquake, the magnitude, I think that was what, a magnitude 1, was fairly close by but deeper. And then there's this other magnitude 3 that was a little bit further away. And so they looked at various measurements, but the one that I want to draw your attention to is the delay time. And so what you can see here, this is in the bottom axis, the delay time suddenly increases about a day before this magnitude 3 earthquake, even though it was a few kilometers away. And then again, the delay time increases less than a day, but a measurable amount of time before the magnitude 1 earthquake. And so this is, a real-time forecasting of seismicity. Now you can imagine, I don't know why nobody's ever tried it, but especially in a place where there are lots of damaging earthquakes, you can imagine putting pairs of boreholes down the fault and just measuring these travel times. And you may not necessarily know how big the earthquake's going to be. I don't know, they didn't really address that. But there certainly are precursors that we can measure. And these are related to the dilation of the material as it nucleates as you approach failure. So these are the kinds of things that would be really nice to measure sort of more regularly. So I'm going to show you an example of something with, well, actually that's the next one. Yeah, so the next one is with a natural source. And this is using solid earth tides and empirical Green's functions as I described before. So we're measuring differential travel times in this study using empirical Green's functions, using solid earth tides as the pump. And this is also in California near the San Jacinto fault system, which is in Southern California. And this is using a seismic array. And this is looking at much more shallow structure, really in the upper few meters to maybe tens of meters. And so in this study, they looked at solid earth tides and differential travel times using empirical Green's functions. And this is just describing in the middle here the different ways that they sort of divided up the tidal strain cycle and measured it in different ways. And what the result was is actually that the travel times were, the materials were slower when the earth was compressed, which is maybe a little bit opposite of what we expect in sort of a dry material. You expect that when you compress a rock, fractures are going to close up and things like that, and it's going to get stiffer. When you're in an area where you have lots of fluids, like in the shallow subsurface, you can have the opposite effect, because when you squeeze on a material, you can dramatically increase pore pressures, and that can actually weaken the material. So in this study, it kind of behaves like the sand on a beach. This is why I have this picture on the right-hand side. If you've ever noticed when you're in the intertidal zone on the beach and you step on the sand dries out around your foot. And intuitively, you might think you're kind of squeezing the water out, but really what's happening is as you compress the sand under your foot, you're actually increasing pore spaces because of the properties of this sort of unconsolidated granule material. And then the water gets sucked into those pore spaces and it appears to dry out on the surface. But that's essentially the behavior they see in this study. And then we can also do this with an artificial probe. And this is, I think, another really interesting study. This is going to show you an example. I had a recording associated with this one that I have to turn off. I don't know if you can hear that. I thought I had gotten rid of all these recordings, but let me see if I can quickly get rid of that. Delete. I don't know. Could you hear that recording?
Before, yes.
Yeah. Okay. Okay. So in this study, I'm going to show you an example. It's still doing that. I thought I deleted that. Let me see.
What if you turn off your sound output during the presentation?
Yeah. I think I have it deleted now. Let's see if I actually did that. Yeah, okay. So what they did was, this is in a cave near the coastline in Japan, and they had a source and a receiver across two different branches of the cave. So you get into the cave on this. This is just my cartoon. Their drawing was kind of hard to follow, so I kind of recreated it. So this is the inside of the cave, and you have a travel time across the rock. So this is what they recorded, and this was based on actually the ocean tides, not solid earth tides, because they're right on the coast. So the water level in the ocean is what's causing the change in stress. So you can see the sea level on the top axes, and then the strain in XX, which I think, I don't know what reference they were using, but I guess the aerial strain is the one that's important, the EXY, and then the differential travel times. And you can see that they're highly correlated. The travel times, the differential travel times are highly correlated with the aerial strain, but it doesn't look exactly the same. It's kind of asymmetric. So if you look at the strains, you can kind of see what the structure looks like. But if you look at the travel times, if you were to take a mean, the mean is not constant. It's higher in some places than others. So essentially, it's highest when the amplitude of the strain, the sort of the peak-to-peak amplitude, is the highest, as opposed to it being a bit more symmetric. So you can imagine that the mean of the aerial strain is pretty constant at 0. You know, kind of over the course of this whole this whole, I think, 14-day period. But the mean of the actual travel times is not constant. It's higher when the peak-to-peak amplitude is higher. So there's some asymmetry here, and I think this is evidence of some fast and slow dynamics. So there is an instantaneous response in the travel times, but there's also this delayed response, or a process that maybe takes longer than a 12-hour cycle. And so that's why we see this kind of asymmetry. So what you can see, if you look at it a different way, what we're looking here is the aerial strain on the horizontal axis and the differential travel time in the vertical axis. These triangles are minimums in the strain, and the circles are maximums in the strain, so dilation as opposed to compression. And you can see there's this kind of linear relationship between the amount of the dilation and the amount of the increase in travel time. So this is just to contrast this with the with the Pinion Flats study, this actually gets, the travel times get longer when it gets extended, which means it gets weaker, fractures are opening up, and when they're compressed, it gets faster. So it's the opposite sign. But there's kind of this linear relationship between dilation and increase in travel time. But on the compressional side, there really doesn't seem to be any relationship between how much the magnitude of the compression and how fast it gets. So it's either there's something going on where there's some sort of a limit to how much it can compress, or I guess what I'm interpreting as there's a time dependence into it, and it takes longer than the 12-hour cycle to actually reach its full compression, or its recovery of the velocity takes longer than the 12 hours that it has. So this is another way to look at it. So in the upper left, we have, this is the magnitude of the strain when it's in, when it's the maximum, and this is the difference in travel time. This is that linear relationship that I showed you before, and this is on the negative side where it kind of there's some kind of a maximum where it no longer, it doesn't keep getting faster even when the peak to peak amplitude gets bigger. And so I don't really like the way that they describe it right here, but what they're saying is that the crack closure rate is faster when the strain rate is slower. And so that means that it's more effective at closing cracks when the strain rate is slower. And so that's the way that they described it, but there is a rate dependence to it. So this tells us that we're thinking about alpha now, that alpha in a nonlinear equation. We're not in the linear regime. We're not in the classical nonlinearity. We're in the non-classical, the hysteretic nonlinear domain. So what I think is, I looked at this quite a bit because this is the most similar to the kind of stuff that I did. And so what I did was I took two different constant strain levels, one that's near the peak when we're on the extensional side, which is in red, and then one constant strain level, which is in the trough when we're most compressional. And then I marked off what the differential travel time was, and then I moved it down here so we can see it better. So I drew a horizontal line, just guide your eye to what is a constant differential travel time. And we can see that the travel times are much slower in the middle when the peak to peak amplitudes are higher. And that's true for when you're at both the extensional part of it and when you're at the compressional part of it. So, but we can see that travel times are shorter when the rocks are compressed than when extended. The rock is softer, meaning that the travel times are longer when the peak to peak amplitude of the strain is higher. I think this indicates slow dynamics. The process of stiffening is slower than the 12-hour dominant period of the strain cycle. So relaxation rate is during extension is fast. So that means it responds very quickly to extension. The relaxation rate is slow during contraction. The period of the strain oscillation is constant, or roughly constant, and the peak to peak amplitude and travel time is nearly constant. So the peak to peak amplitude and travel time is primarily determined by the relaxation rate, not the strain amplitude. So what I'm saying is that the peak to peak amplitude here and the travel time doesn't change very much, where even though the peak to peak amplitude in the strain does. And so I'm interpreting this to mean that the peak to peak amplitude and the travel time is determined not by the strain amplitude, but by the relaxation rate. So how would this behavior work in an anisotropic stress field like that in the Earth's crust? So as we know, in the Earth, we have an SH max and SH min. Those are the maximum compressive stress and the minimum horizontal compressive stress. That's kind of, in the Earth, it's often described in the opposite sign as what I would sort of do in the laboratory. So SH max is the maximum compressive stress rather than maximum extensional stress, but we'll just go with that. And so if we look at the tectonic stress just as a some basic parameters. We're talking about megapascal scale. So tectonic stress in the upper crust is on the order of a few megapascals, maybe tens of megapascals. This is the horizontal stress, the horizontal differential stress. It's cyclically anisotropic over the periods of time that we're going to be measuring. It's constant. Of course, it does evolve over long periods of time, meaning like years to decades to centuries, things like that. Tidal stress is more on the kilopascal scale, so 1 to 2 kilopascals. It's almost isotropic. It's greater along an axis pointing at the place on the Earth closest to the moon or the sun by a factor of about 2. It sort of depends upon the latitude and things like that. And it alternates between compressive and extensional. So if you can think about fractures in the Earth, fractures that open perpendicular to SH max and the tectonic stress field will always tend to keep them open. So if you imagine these fractures here that are aligned kind of with SH max, or that open perpendicular to SH max will tend to try to keep them open because it's squeezing in that direction. And then if we have fractures that open parallel to SH max, the tectonic stress field will always try to keep them closed. So if you imagine these fractures here, they always try to keep them closed. So what I'm imagining here is that in response to the tidal compression, these cracks will creep faster. So in other words, when fractures are kind of opening and closing slightly or becoming weaker and stronger due to the tidal stresses, and fractures in this orientation, when they're closing, they're assisted by the tectonic stress, and fractures in this orientation are opposed by the tectonic stress. And so I would expect them, the relaxation rates to be different. So faster over here, slower over here. So then we have this stress-induced anisotropy in behavior. So the peak-to-peak amplitude and travel time is primarily determined by relaxation rate, not the strain amplitude, according to the results we saw in Japan. When we measure the changes in the peak-to-peak amplitude and the travel times, we are really measuring changes in relaxation rate, not the changes in strain amplitude. So we would expect the relaxation rate to be faster in the orientation of SH max because of the differential stress field is helping out as opposed to opposing the relaxation. And we saw that the relaxation rate and extension is essentially instantaneous. And so I wouldn't expect the behavior on the extensional side of it to be any different. So we're going to apply the pump probe method in the Earth. We measure differences in travel times in the coda portion of the empirical Green's function. One Green's function is calculated from extensional periods and the other is calculated from compressional periods. So this is sort of a schematic. We have tidal forcing. It isn't uniaxial like this, but this is just kind of a schematic. And then we have a probe wave that's about a 5-second period wave. That's some combination of surface waves and body waves. The period of the pump is about 12 hours, but it varies quite a bit from cycle to cycle. So what we do is we divide real time into periods of time when the Earth is extended. I'm just showing an example. The red vertical lines are the beginning of one of these periods of time, and the blue lines are the end of one of these periods of time. And so we have a whole bunch of these. And then we do the same for the compressional side. And then we compute empirical Green's functions from each of these two. And later on, I'll be using the neutral part as well, but I'm not using it in this part of the study. I have an automatic advance going on too that I should have turned off, but I didn't. But so what I'm doing is measuring the difference in travel time between the positive and negative parts of it as a function of azimuth. And so the parts, at a particular azimuth, I expect that the difference in travel times to be biggest in SH max because the relaxation rates will be the fastest. as I showed both in the Japan study and also looking at how an anisotropic stress field would affect, I think, what the results are in the Japan study. So we are measuring the velocity when the Earth is in compression relative to an extension. The fractional velocity change is greatest in the direction of SH max because relaxation is faster. And by using different subrays, we can detect small regional differences in the stress field. And so essentially what we do is we measure the difference in travel times as a function of azimuth, and we can fit a sine curve to it, and then we can measure what the predicted SH max is. And so this is using different subarrays, we can try to predict what the stress field is. And so in this little map here, the stress indicators are from borehole and earthquake focal mechanism inversions and things like that. And this is the measurement I get by measuring the stress-induced anisotropy. And they're actually very close. They're within a few degrees. It does get a little bit messy because there are other things I think that affect this measurement, including things like pore pressures that have nothing to do with at least the anisotropy in the stress field. But because you're fitting a sine curve, I guess you make the assumption that it's a sine curve because in a stress field, as you rotate around, your probe, it would look like a sine curve. We can actually get a pretty good estimate, even though there is some noisiness in the actual measurements. Okay, so that's looking at one application. A second application is how does nonlinear behavior indicate damage properties in a fault zone? Ultimately, I would like this to look at the evolution during an earthquake cycle. Of course, in Parkfield, as some of you may know, there are magnitude 6 earthquakes every approximately 30 years. So it's kind of a good area to study. There are others. The North Anatolian Fault is another one. But we could look at how nonlinear behavior changes over the course of an earthquake cycle. I'm not doing that yet. I'm just looking at how it varies with different regions of the fault zone. So this is a seismic array around Parkfield, California on the San Andreas Fault. And I'll be looking at different paths between different stations and where they are in proximity to the San Andreas Fault. So we're going to recall some of the what I talked about earlier as far as different kinds of things we may expect to see. We often use linear elastic measurements to infer material damage or other properties related to damage such as permeability and pore pressure. However, the nonlinear elastic parameters are much more sensitive. We saw this equation before where the stress is related to what I'm calling here the apparent linear modulus plus higher order terms plus its alpha term, which brings in the dependence on strain and strain rate. So we're going to try to measure more of this alpha parameter. The alpha parameter is actually related to this hysteretic behavior or the size of this loop, or I guess the amount of area inside the loop, you could think about it. And so we could think about this alpha and beta parameter and what it would look like if they were 0 or non-zero. In this axis, I have the strain on the horizontal axis and the modulus on the vertical axis, or the delta M over M, so the change in modulus. So up is faster, down is slower. A linear system would just be a horizontal line. That's where alpha and beta are 0. If alpha was non-zero but beta was 0, we would have a hysteretic behavior, but it would still be horizontal. If beta was non-zero and alpha was 0, we would have a line that was inclined, and then if they were both non-zero, we would have something that kind of looks like this, where we have a loop and it's at some kind of a slope. So this is really how I'm going to be measuring it on the San Andreas Fault. Now, I don't have the temporal resolution to actually get every point on this loop, but I can get a few points and constrain at least some plausible hysteretic curves that are occurring in the rocks around the San Andreas Fault. So it's the same kind of method that we did for the Oklahoma and New Mexico study, but this time we select periods of time with negative, neutral, and positive strain and strain rate. So it's so we really have 6 different bins of different strains, and so we can calculate separate empirical Green's functions for each of the 6 bins, and then we can use those to sort of construct I guess hypothetical hysteretic curves, and you know, by measuring, and so we're measuring travel time differences for 5-second waves, so this should be sensitive to the upper few hundred meters to a few kilometers. And again, this is looking at the CODA part, as we usually do with differential travel times in with empirical Green's functions. And then we can look at different station pairs to look at different regions around the fault. So I divided into 4 different groups of pairs. So we have exterior paths, which is the red. So this is looking at regions on the order of, you know, maybe a few hundred meters to a few kilometers away from the fault. We have crossing paths, which is a little bit more of an average. We have all paths, and then we have interior paths. So kind of in order, this is the most exterior, second most, third most, this is the most interior. So we can look at these 4 different sets of stations to get an idea of different regions around the fault. Again, using different strain bins, both in terms of the strain magnitude and the strain rate, to get different parts of the hysteretic cycle. And this is a cartoon. The stars, what I'm showing you here, are the actual measurements. They're the real measurements with the real magnitudes. And then the lines that I've drawn are hypothetical, just possible hysteretic curves, and I'm basing that both on the upper part of this, that's related to the strain magnitudes, and on the bottom it's the strain rate. That gives you essentially which the strain rate measurements give you the direction of the loop. So I have added arrows here that tell you which direction this is traveling in terms of this is a strain modulus plot. And then the magnitudes tell you how much of a slope. So I'm not measuring every point along these curves. I'm just drawing a couple of hypothetical curves that are consistent with my measurement. And so this gives you, on the lower right, it gives you an idea of what part of the fault we're measuring. So the light blue or the teal or whatever you want to call this, what is it, cyan or whatever. I don't know my colors very well. That's the closest to the fault. We have the blue, which is slightly further away, and the red is furthest away. So this is the interior paths, crossing paths, all paths, and exterior paths. And we can see a change in evolution of behavior as we get more to the fault core. So we can see that velocities are slower when the Earth is in extension versus when in compression. That is consistent with what we see generally in Oklahoma and New Mexico, although we do see some of the opposite behavior there as well. The velocity difference between the 2 cases increases with the decreasing distance to the fault, so that indicates increasing damage. So for all but interior paths, the Earth is faster when compressing versus when expanding. So that's the strain rate part of it. And for the interior paths, the Earth is faster when expanding versus when compressing. Now, I don't have a really a good explanation for that, but we do have some experimental results on laboratory rocks where similar kinds of things are observed. And I'm not even sure sometimes in laboratory rocks, we know what's going on, but I think with further both laboratory experiments and experiments in the Earth, we may be able to connect those things to kind of the physical processes. So this is really kind of the summary, that we detect increasing material damage with decreasing distance to the fault. Both beta and alpha must be non-zero. And by improving the time resolution, we will better be able to constrain the magnitudes of the nonlinear coefficients, beta and alpha. And so that's really the goal, that we want to be able to constrain more of this elastic equation, more of these parameters that are related to the elastic modulus, the nonlinear, hysteretic elastic parameters. We can compare this to laboratory studies, as I said. The reason why I plotted these this way in terms of the strain versus modulus is this is how they do it in laboratory studies. So these are just different kinds of rocks, and these are the loops that we see in the laboratory rocks. And the reason why, these are two different possible examples where we have kind of a crossing paths, a loop that doesn't have that doesn't cross itself and one that does. In my results, I can't tell the difference because I don't have enough sort of temporal resolution, but we can see that in laboratory rocks, they often see this. And so it's at least the plausible behavior that we might be seeing in the earth. And so I can compare these, and it looks an awful lot like some of these materials here, like this, like this granite or something like that, especially. It looks kind of like, if I'm looking at this right, it actually kind of looks like this one, the crossing paths, because of the way the direction of the loop. So we can do these kind of comparison to laboratory rocks to try to get some understanding of what we might be seeing. There's also some other kinds of in situ studies. This is an example of using one of these vibroseismic trucks that they use in seismic hazard kinds of analyses to study the shallow subsurface for trying to constrain what strong motion amplifications might be. And these are some results from looking at the shallow subsurface excited by one of these trucks. And so the left-hand side is really what is comparable to us. This is the right-hand side is attenuation, which I'm not looking at, but this is the same kind of a plot where you strain on the horizontal axis and elastic modulus on the vertical axis. And so actually this looks a lot like this one up here. It's not really crossing, and the direction is counterclockwise. So our results kind of look like kind of this this upper right one with the crossing paths. So again, we don't necessarily know what all this means yet, but we can at least compare to what is seen both in situ in the earth, kind of in these controlled studies, and also in laboratory rocks. And I think doing a combined sort of combining these passive studies, like what I'm doing in the earth, to other kinds of studies, we can maybe learn a little bit more about what we're actually seeing. So that's going to wrap it up. So my conclusions really are that rocks are nonlinear elastic materials. I guess everybody in this group knows that. Nonlinear behavior is due mostly to internal contacts, such as grain boundaries and fractures. Most of the properties, or at least many of the properties that we care about in geophysics, happen at the internal contacts, such as material failure, fluid and solid interactions, things like that. And we can probe the behavior of these internal contacts by measuring nonlinear behavior. So that's the end of my talk, and I'd be happy to entertain any conversation or questions or whatever it is that we want to talk about.